Hi there. Welcome to Eduretics, where we make your high school life simple. I'm Aniket, and in this part of the conceptual mathematics playlist, we're going to talk about exponential functions. I'm going to take you through each and every bit of what exponential functions are and how to represent given scenarios through exponential functions. That's a really important aspect from testing point of view. This is a very popular topic on the SATs, the ACT, and GCSE even, and even on AP Calculus. This is a popular topic. Okay, so let's begin. Okay, so before we delve into the direct mathematics of this, let's talk about a scenario. So there is an apple farm. Let's say you're given that information. There's an apple farm, and every year the produce from this farm doubles. Okay, so every year the apple produce doubles. This is what is given to you. Okay, and another information which they've given you is that in the first year the produce was, so first year the produce was, let's say, 40,000 apples. This was the produce in the first year. Now they're asking you what would be the produce in, let's say, the 8th year. What's the produce in the 8th year, and what will be the produce X years from now, or X years after the first year. X years after first year. Okay. Now pause the video here. Try to think according to like your own ideas how we could form a mathematical expression to represent this scenario, this situation. Okay, so let's decode it one by one. First year we have 40,000. Okay, 40,000 in the first year. Now let's say in the second year, how much would we have? It is doubling. 40,000 multiplied by a 2. In the third year, it's going to be 40,000 multiplied by a 2. This is the second year value multiplied by a 2. Fourth year, 40,000 multiplied by a 2 multiplied by a 2. This was the third year value, again multiplied by a 2. So if I were to represent these values in powers of 2, you see, I can simply write for the second year it's 2 raised to power 1, the multiplication. For the third year it's 2 squared. There are 2 2's getting multiplied. For the fourth year it's 2 cubed. 40,000 multiplied by 2 cubed. And for the first year I can write 40,000 multiplied by 2 raised to the power of 0. Okay, this can be written for the first year. Okay, now can we formulate a function from here? We can, right? So let's say 40,000, this is a constant, 40,000, and then X years from now it will be 2 raised to the power of X minus 1. So when you put X is equal to 1 for the first year, it's 40,000, like that. Okay, so this becomes the apple produce P. This is what is called an exponential function. You just wrote your first exponential function. Okay, so this is an exponential function. If I replace 40 with a k, 2, this base with an a raised to the power x minus 1, let's say x minus 1 can be written as a t. I can say t, and t is equal to x minus 1. So p is equal to, or p of t. Now p becomes a function of t, the number of years passed. So p of t is equal to k a raised to the power t, where t is the number of years elapsed after first year. After first year. Okay, this is the t, number of years elapsed after first year. Okay, so P of t is k a raised to the power t. Here k is given the name of a coefficient. We call k as a coefficient. It's mostly a representation of the initial given value. A is basically the base or You can also call it as a multiplication factor. Okay, multiplying factor. T is the power. That's the exponential function for you. That's the general representation, k a raised per x, or you can write it like this: f of x is equal to k a raised to the power of x. Okay, so this is the basic of exponential functions. Now let's look at some other scenarios. I'll pick some real questions from tests to show you like how to do it quickly and how important this topic is. Okay, here's a question. According to Moore's law, the number of transistors included on microprocessors doubles every 2 years. In 1985, a microprocessor was introduced that had 275,000 transistors. Based on this information, in which of the following years does Moore's law estimate the number of transistors to reach 1.1 million? Okay. This is actually, I would categorize this as a hard level question, looking at the level from SATs. Okay. Otherwise, it's a medium difficulty problem. Okay. So here we're going to make use of exponential functions. As you can see, it's doubling every year. So we did a similar scenario just before this, the Apple one. Okay. So in 1985, they've given us that there was 275,000 transistors. Okay. Now every 2 years it's doubling. So the next thing in 1987, it's going to be 275,000 times 2. 1989, it's going to be 275,000 times 2 squared. So as you can observe, we're getting an exponential function of this form, k a raised to the power x, where k is 275,000, a is 2 raised to the power x. This is the number of transistors T. Okay, but the only change here, or the only thing to be careful about here, is x increases by 1, number of years increases by 2, because it's doubling every 2 years. Okay, so now for 1987, we can see 275,000 times 2, or just put x is equal to 1 for 1987. This becomes a 550,000. You can check on your calculator as well. Okay, and then when x is equal to 2, that would be 1989. This would become a double, or 275,000 multiplied by 4. This gives us 1,100,000. Okay, that's exactly 1.1 million. That's what we asked. So option B is the correct one, 1989. So now you're pretty adept with forming exponential functions when you're given the exact multiplication factor, like doubles every 2 years, or triples every year, or becomes 4 times every year, like that. Those kind of things, I am assuming that is clear now. Okay. The next one is to deal with percentage increase and percentage decrease. Let's check that as well. So let's look at a few scenarios where there's percentage increase and percentage decrease. Okay. This is mostly used in the financial world. So when we do financial calculations, we'll be dealing more with percentage than with direct multiplication factors, because the usual financial instruments don't give returns in like direct multiplication factors. Those huge returns are not possible so easily. So we have percentage calculations. Okay. So that's just one example, the financial thing. It could be anything. So let me take a scenario. Say you have some k amount. Okay. This k amount, maybe let's say $50,000. Yeah, $50,000. Okay. Now you give it to a bank. Okay. You give it to a bank, and that bank gives you let's say your value, the value of this amount, initial amount. The bank gives you a return of 10%. That means this value increases by 10% every year. Okay, I'm not talking about the interest here. I'm saying this value itself increases by 10% every year. Okay, so what would be the value after X years? And for that matter, let's say 5 years. Okay, so how to represent this situation? You'll again write plain and simple. First year is $50,000. Second year, careful, 50,000, this is there, plus 10% of 50,000, because the initial amount plus a 10% increase on that. It's giving a 10% increase. The amount is increasing by 10% every year. So it will increase by 10% of itself. Okay. So basically this is the value coming from the first year. This is the increase happening. Now this will become the default, the initial value for the third year, and that will increase by 10%. You see the chain? Okay. So how do we figure this out? So for the second year, I can write by simplifying 50,000 I can take outside as common, 1 plus 10 over 100. Okay. 50,000, 1 plus 10 over 100. Simple algebra. So 1 plus 10 over 100. 10 over 100 is a 0.1. So this becomes 50,000 times 1.1. This is the value for the second year. Okay. Now for the third year, this becomes the initial value. 50,000 times 1.1. Okay. And then this whole thing increases by 10%. So I can definitely write directly 1 plus 10 over 100. The 1 represents this original value, this complete value. 10 over 100 represents an increase of 10% on this value. That's why it's outside common. It's getting multiplied to both. Okay. So now what does this become? 50,000 times 1.1 times 1 plus 10 over 100, 1 plus 0.1, again a 1.1. So third year, you see 1.1 times 1.1. Let's look at the fourth. For fourth year, this complete thing will come down. Okay. So 50,000 times 1.1 times 1.1. Just be patient a bit. I know this might be irritating for some who've already done this topic, but it's really important to go deep and see what's exactly happening. 1 plus 10 over 100. Again a 10% increase on the third year value. This adds another 1.1 to the multiplication. So 50,000 times 1.1 cubed. Now we're talking. So this is where we arrive. For fourth year, it's 50,000 times 1.1 cubed. For third year, it's 50,000 times 1.1 squared. As you can see, two 1.1s are there. 1.1 squared. Second year, 50,000 times 1.1 raised by 1. First year, 50,000 times 1.1 raised by 0. Able to establish a pattern the way we were doing the last transistors question. Similar to that, we're doing here. The only difference is the multiplying factor is a bit different. It's not a whole number. It's not a big number. Okay, that's just a slight increase. Okay, so the function we're getting it at is for the amount after X years, it's going to be 50,000. This is the initial value times 1.1. This is the base of the multiplication factor raised by X minus 1. Okay. Now an important thing which I would like to clear here, okay, is that this AX, like the value, the amount, or the value of the amount, that can be represented by both of these expressions. 50,000 times 1.1 raised by X minus 1, or 50,000 times 1.1 raised by X. How? Look very carefully. Okay. So when I use the first one, it is totally dependent on the reference that I'm taking for counting the X's, the years. Okay. So for X minus 1, I'll say I'm taking the beginnings as the reference, beginning index as the reference. Beginning index as the reference. So beginning of first year, X is equal to 1. Beginning of second year, X is equal to 2. Beginning of third year, X is equal to 3. Okay, these are beginnings. So we're doing X minus 1. Why X minus 1? Because beginning of first year, you've just deposited the sum, the 50,000 amount. There has been no change in it. So X is equal to 1, but X minus 1. So this would eventually be a 0. Okay. So the value I'm getting at X is equal to 1 for the first expression would be the value, same value which I'm getting at X is equal to 0 for the second expression. As you can see, these would be equal. Why? Because for the second expression, 50,000 times 1.1 raised by x, the reference is ending. So end of first year, x is equal to 1. End of second year, x is equal to 2. End of third year, x is equal to 3. Okay? So you know how they correspond. This corresponds to this. This corresponds to this. X is equal to 4 would correspond to this, because ending of third year is also equal to the beginning of fourth year. But the values of 3 and 4, the x's are different. Accordingly, we've adjusted the power. That's the only difference. This you need to understand like properly, 100%, because this will solidify your understanding. You don't need to memorize anything. Okay, you don't need to memorize whether I should always use x minus 1 or x. You should take your call then and there whether you want to represent the beginning index or the ending index. Okay, they might ask you that, tell the value of so and so product after n years. So when they say after n years, it's better to take the ending index. So you can directly take x, and then when you put the value of x as n, it will automatically become the value after n years, like after the end of n years. Okay, so that's the only difference between these two representations. They represent the same thing. Okay, let's move on. Sometimes you're given direct functions which are written like there are no scenarios but direct exponential functions, and you need to figure out what's happening. That's the opposite of what we just did. We converted the scenario into an exponential function. Next, we need to see an exponential function and then decode the scenario. So for example, you're given that a car's value changes per year according to, let's say, this function. So please excuse my handwriting. So according to, let's say the value is represented as v of n after like n years, and I say 180,000. Okay, 0.64 raised to the power n. Okay, so in this function we need to decode what's exactly happening. Is the value increasing, decreasing? Was the initial value? Let's check all those things. So per year it's saying like after n years the value is this. When I take n is equal to 0, that means after 0 years, that means just at the beginning of the purchase of the car, I put n is equal to 0, I get, so when this becomes a 0, 0.64 raised per 0, any number raised per 0 is a 1. So I get v as 180,000. That means this is the initial value of the car in dollars. Okay, initial value of the car. At n is equal to 1, I see 180,000 multiplied by 0.64 raised by 1, or simply as 0.64. Now since 0.64 is less than 1, this value is going to come less than 180,000. So you can see it's decreasing. That's for sure. Then n is equal to 2. You see v is 180,000 times 0.64 raised to the power 2, or 0.64 squared. Okay, so that means it's further decreasing. But now we need to find out the percentage decrease. Okay, so that's the important aspect here. I'll tell you a quick shortcut after I explain to you what exactly this is. Okay, so let's say 180,000 is a k. That's a k, initial value k is getting multiplied with 0.64 raised power n. What is 0.64? So to give you a context, in the last question it was increasing by 10% every year. The value of that amount which you had invested with the bank, it was increasing by 10% every year. So what had we arrived at? K times 1 plus 10%, which had eventually given us k times 1.1. What if here, which is quite obvious that it's a decrease. So k times 0.64 can be written as 1 minus 0.36, or 1 minus 36 over 100. Now I think it's becoming clear. 1 minus 36 over 100. 36 over 100 means 36%, and 1 minus means a 36% decrease every year. Okay, this is a 36% decrease every year. That's what this exponential function was meant to represent. Okay, so now let's see how we can quickly decode this, okay, for a given scenario. So someone says, let's say there's a factory. In 2007, the factory's value is $1.1 million. Okay, $1.1 million in 2007. Okay, every year it's increasing by 12%. 12% every year, the value. After n years, what's the value going to be? Quickly write an exponential function. Try it out on your own. So let's do this. Let's say the value is V, or factory F. F is equal to 1.1 million. Keep it outside. That's the K, times 12% increase. 1 plus 12%, quick, raised by n. 1.1 times 1.12 raised by n, or 1.1, 1.12 raised by n. This is the final value in exponential functions. Okay, this is how you can quickly write it. Okay, just be careful. I don't think I need to explain that logic again. Like, should we use n or n plus 1 or n minus 1? That totally depends on what starting point you're taking and what references you're taking. Are you taking the beginning of the year as the index of the new year, or the index of the year that passed? Okay, so that's a point of reference dependent. Okay. Okay, next, let's say the population of tigers in a forest is decreasing by 24% every year. It's decreasing by 24% every year, and in the beginning it was 12,000. After 10 years, what is it going to be? Quickly, so 12,000 times 24% decrease, 1 minus 0.24 raised by n. 12,000 times 0.76 raised by n. N is equal to 10. And there you go. That's how you can quickly write exponential functions. You can write scenarios as exponential functions as decoded scenarios. So this is all about it. Now make sure to practice from the non-linear functions videos in the digital SAT playlist. Okay, so whichever test you might be appearing for, just it'll be really good for practice. So head to the digital SAT playlist, and there the non-linear functions videos. Go for only the hard ones if you like. Okay, just the hard ones, and practice from there. Okay, in case there are any questions, any doubts left, just throw them in the comments, or send it to me in email. If you want any personalized classes, you can book from my EduRetics website. Thank you. Bye-bye.